I'm going to let Juan Antonio Valiente Kroon talk about conformal studies of spacetimes with xAct.
It's a pleasure to tell you a bit of what I do with xAct. So I have this fancy name of Conformal Explorations of Spacetime with xAct. And so what I want to describe is not really a package, but I guess the way you could use xAct in a big, large-scale project. And the large project I want to tell you about is the following. So some years ago, 8 years ago, I published a book. You can see this, so some sort of advertisement here. So this book is Conformal Method of in General Relativity. So some of the people who hang around with me know what this is about, but this is new for you. So this book goes about certain equations called the conformal Einstein field equations. So these equations are a conformal representation of the Einstein field equations, which allows you to study global problems, so existence and stability, and also study of asymptotics using a compact manifold, so using Penrose's idea of conformal compactification. Okay, so if you go through this book, then there are, describe some of the main milestones in the field, right? So some of these, which I have summarized here, but this is not really just to give you a taster, is the global stability of the Sitter spacetime, semi-global stability of the Minkowski spacetime, construction of the ADS spacetimes, for example, in string theory, and also the analysis of partial infinity, right? So these results are not original of myself, right? But then now this book, what it does is it gives you a unified view of all these results and collecting results from this. It's more like a literature overview. Okay, of course, right, to write this book, I have to go through a huge amount of literature, and somehow that happens. I did most of the calculations of this book by hand. So also, mind you, this is a book which is around 600 pages. And after I finished the book, so I already, so as I said, this book was published in 2016, and I was already, I would say, an expert user of xAct at the time, but somehow, because of time constraints, I just decided that the simplest way to keep this book and finish this on time was doing it by hand. But I think I was wrong. So after I finished the book, I then realized that actually it would be very nice to actually have a companion, a computer algebra companion of this book. And I have spent some years afterwards trying to do that precisely. And so why you wonder why? So why we really need to have, so you have this book, why you need to have an exact version of this? Well, so first of all, obviously, as I said, so all the calculations were done by hand. Of course, most of the calculations were in the literature, but then, of course, conventions and notation and so changes. And so it's actually, if you really want to use this book to make it be useful, really you have to be sure that the correctness of the equations, right? And if you do it by hand, well, there is always this question, right? The other thing that happens is that there are a lot of formalisms being used in this book, right? So there are many tools, which I will talk about a bit more later on. So like metric formulation of the equations, frame formulations, spinors, and so on. And then you want to compare things in an easy way, right? And as you will see also, so some of the mathematical arguments, although there are some theorems that use abstract arguments from PDEs, nevertheless, to make use of these PDE techniques, you also need to do some involved calculations. And this is an invitation to do computer algebra, right? And then, of course, I think the book is intended to be as a starting point to develop the area further, right? And then, of course, you may think, look at a theorem or a technique in the book, and then you would like to extend this, right? Then I think nowadays the best way is to do that with computer algebra. You may also think that this is, you may want to implement numerically some of the equations. Then again, I think even in numerical applications, it's even more important to be able to to be sure that your equations are correct. So then of course, again, having a exact version of this is essential. And then something, for example, that is also very relevant for my own research, so doing asymptotic expansions. And then xAct is a very natural starting point to do this sort of approximate methods. Okay, so as I said, so the book is 600 pages, and then there are a lot of involved mathematical arguments, but there is, I think, a common thread. And of course, also, what sort of things you would like to do in xAct? Well, so one of them is to derive key equations. Then the other thing is that you want to apply methods of partial differential equations. And then, so applying this methods of partial differential equations, requires often to bring these equations that you have derived to a certain standard form where you recognize that equations are hyperbolic or elliptic. And then again, the computer algebra xAct is ideal for this. So then, as well, so also some of you who know about the sort of questions on initial value problems, so there is the propagation of the constraints, right? So when you do an hyperbolic reduction, you have to drop certain equations, and then you have to verify that the evolution equations preserve these constraints. And this is somehow tied as well with the integrability condition. So this requires a huge amount of tensorial or spinorial calculations, which, yeah, again, not naturally done with xAct. Yes. So these are examples of sort of things you would like to do. Okay, and also I guess a disclaimer. So I have learned quite a lot. Well, quite a lot. In fact, everything I have learned from xAct is through interaction with and collaboration with Alfonso Garcia Parrado and Thomas Bagdal, right? So who have taught me everything I know basically on xAct. So as you will see, so I will show you somehow an idea of this implementation of my book in xAct. And so this requires quite a lot of packages, right? So in particular, I'm using Extensor, of course. So xAct to extract equations and put them in a nice way in LaTeX, Xcova for component calculations, C manipulator, and also the package Spino. So there are really essential tools for what I want to show to you now, right? So then with this, then I move into my the notebook I want to show. And so this is the implementation of the conformal lifetime field equations. And then also I think some credits. So this is actually I think built on a very early version of a notebook that Alfonso did, and he brought to my attention that you could actually do what I'm going to show you. So just to give you some historical context, so it's probably more than 12 years ago. So I gave some course on the subject of this book. And then so Alfonso was one of the attendees of this course. And then I discovered that every afternoon after I was doing the presentation of this course, so it was, I think, a couple of weeks, Alfonso was going and doing implementation of deriving the equations with xAct. So this really was an eye-opening experience for me, right? And then somehow I took on what he did and somehow tried to follow his philosophy. Okay, as I said, so this implementation of my book, right? So this is not complete, right? So and in fact probably it would never be a complete, so something that you could fully complete, right? But then I add on things that I require in the sort of in my upcoming ongoing projects. So you have to load, as I said, xAct and text xAct, and then, well, so as usual, so you define a form manifold, right, where you're going to work. And then for those of you who know the philosophy of working with conformal methods and conformal compactification a la Penrose, so the point is that you don't work on the physical manifold where you satisfy the Einstein equations, but rather in a conformally compactified version, right? And the notation is that the physical spacetime carries on some tildes, or every quantity associated to the physical manifold carries tildes, while those on the unphysical spacetime, which is obtained by the conformal compactification, doesn't contain the tildes, right? So then you define your then you also define the metric on the physical manifold, right, which carries a tilde, as you can see here. And also there are a lot of checks. And then it turns out that besides this, you can also obtain some generalizations of these conformal field equations that actually are not associated to Levi-Civita connections. So there are more general structure called a Weil connection. So it's a connection which is torsion-free, but not necessarily metric. And you can also do this sort of consider this sort of connections or covariant derivatives in xAct, right? So it turns out that really, so xAct already has built in all these ideas to study conformal transformations, right? And then what is nice, and this is what I somehow learned from Alfonso, is that you don't type in the equation that you want, but then really you start very basic with your conformal transformation, right, between the physical metric that define the Einstein equation and the non-physical one, and then you go step by step deriving everything, right? In particular, so you compute the transformation between covariant derivatives, right, from scratch, right? So then this gives you a setting which is completely self-consistent, where you don't have to worry from borrowing pieces of equations from different origins, or where there may be some clashes of notation or conventions, right? And then you go on, and then using standard tricks, right? For so you can do this as you were doing this by hand, step by step, derive somehow the transition tensor, right, that connects the two connections, right? So it's given in terms of derivatives of the conformal factor. And then you go on. So once you have this transformation rule for between connection, then you can also compute a transformation between the curvature, right? So this is somehow essential in this program of conformal field equations. So xAct has already built in, given two connections, tells you somehow the formula that tells you how to connect the two curvature tensors. But in terms of transition tensor, but then what it doesn't know is actually the actual value between the transition tensor, right? Which we already have computed, and then you go on, so you can specialize the transformation formula for the Ricci tensor, right? And then also for the Ricci scalar, right? So I think what is beautiful from this is that, so you can actually do this almost as if you were doing the calculation by hand on your notebook, right? So this to say that, right, that if you don't know how to do the calculation by hand, right, on paper, you will not be able to do that, right? So, directly in the computer, right? So it's really the xAct really is really the tool here to make the calculation efficient, right, and to make sure that reduce the amount of mistakes that you can possibly do. And then again, as I mentioned, so some version of these conformal equations require these Weil connections, and then again, there is a transition tensor, right, between the physical connection, covariant Levi-Civita connection, and the Weil connection. This can be also again derived from scratch, so using somehow standard techniques, right? And then you go on, and then you can compute somehow. So the more complicated relation between the curvature of a Weil connection and the curvature tensor, right, of a Levi-Civita on physical metric. So on. And then also there are other objects, so the Schouten tensor and so on. This is probably not so important for the discussion, right? But there are some other associated objects. Then again, so something that plays a role in the discussion are obviously the Bianchi identities, right? So there are relations that are used recurrently, and then you can actually derive them from scratch, right? So that and I think this is also something very nice, right? And somehow consistent with this philosophy of having a self-consistent world, right, when you are operating. Okay. So this is somehow, as you see, there are a number of so this just section is really about deriving somehow the basic relations. And then I guess somehow what is key is, well, so you can also derive the key equations that are used in my book, so namely these conformal field equations, and then somehow the most simple vanilla version of those are the so-called metric conformal field equations. And then again, so this notebook gives you a derivation of the equations, right? So these equations start from the transformation rule from the Schouten tensor. So it's basically a trace reverse version of, or trace modified version of the Ricci tensor, which somehow naturally appears in conformal geometry. And then starting from that transformation, then there are a number of steps where it allows you to rewrite this equation somehow, the transformation as somehow a conformal equation, right? And then this allows you to identify certain new quantities that have to be defined, and that you define as you go, and then you have obtained nicely the first equation, right? Which is somehow the only, is basically the transformation rule between, for the Ricci tensor somehow in this guise, and then so on. So then you can construct all the other equations. For example, what we call the second conformal field equation is a sort of integrability condition from this equation. And then as you do, so you take covariant derivative, you do commutation. So you, because the covariant derivative equation, you commute, and all this operation, right, of commuting, covariant derivatives, and so on, substituting definitions that are done by xAct very nicely, and then you're having now the second equation, and then so on, right? So you do the other equation, right, which involves the Bianchi identities, right? So, and this gives you an equation for the Schouten tensor, and so on, and then so on. Okay. So again, I guess what I want to show to you, right? So is that really, so once you have done this and you have derived your basic equations, then well, you are sure that they are correct, right? So and then you are self-consistent, and then you can go and do more complicated things, like, for example, compute. So it turns out that from this equation that I have shown you, you can actually derive wave equations for the basic fields, and then this is something that already involves more heavy computer calculation, where you somehow have to commute, apply covariant derivatives, commute many times, and so on, and then this can be done in a very clean and effective way here, right? So I think that the other bit, I think that is crucial here, and xAct does it beautifully, is the following: is that it turns out that when you are trying to have a project with these conformal field equations, in fact, you don't use this basic formulation of the conformal field equations. I think I will not go into the reasons for this, but in fact, you need like a pepper up or power up version of those, and one of these versions that people use, or we use, is to have a spinorial expression, right? And then, so for this, so one uses this package spinors, and then also C manipulator, and then so what you can take, so again, so you can define the spin structure on your manifold, right? So this is something that is somehow built into spinors, and then well, so you can again check all your conventions and so on. But so if you start from your basic to the equation, say like the first conformal field equation that I showed before, then there are a number of instructions, right, that allows you to transform this equation in a very clean way to its spinorial form. And then once you have it in this form, then you have well, all the powerful tools that spinors allows you to do, in particular making use of reducible decompositions and yeah. So, and then this is done really cleanly without having to type in the equation, right? And then you can do this in yes, as I said, by hand in a very clean way. And just, I think I would like to show you is say the last one, so which is somehow the most famous one is the Bianchi equation, right? So given this rescale Val tensor, right, which is one of the key variables in this setting, so you cannot use this all the packages in xAct to obtain the spinorial version, right, which is written into the counterpart of D, which is a symmetric spinor. And just I guess as a last example, so it's well known somehow in the literature, although quite cumbersome, that from this equation, it is possible to derive a wave equation for this symmetric spinor phi, right? And then, well, this is also, again, something that demonstrates the power of xAct. So if you try to do this in by hand, well, it's a calculation that you can do, right? But then in xAct, right, it's just a number of steps here, right? 10 steps, right? And then you obtain beautifully this wave equation for the valve spinor, right, in a very clean way. Okay. As I said, so I think at the core somehow somehow this shows the philosophy, right, that I was trying to explain to you, right, of trying to codify the book, right, that I showed to you. And then, of course, as I see, the point is that, so this notebook here now, if you have a particular project that you want to undertake, right, so you can take the question from here, right, and take it from there. And maybe see if there is something else that I would like to say. Well, I just say that, so something that is also very important is that you like to do, say, given this conformal field equation, so you can also do a 3+1 decomposition, right? And then this is also something that you can do with quite conveniently, efficiently in xAct, right? So there is a whole section on how to do this, and there is also, I guess, for the more experts in spinor, so there is also say spinorial version of the 3+1 decomposition that we call the space spinor formulation, right? And then so again, so the beauty of this is that because of you have everything integrated in this notebook, so you can make use, so translate between formulations very, very easily, and yes, and translate and use information, right, from different approaches in a very convenient way, right? So yes, I think if you really have a very big project, say like this one, right, where you have several formulations of certain of your favorite equations, I think this is really the way to go, right? So yes, I guess, as I said, just to conclude, right? So I think I wish I had done that before I had written my book, right? Maybe it had taken me some time, taking longer to finish the book, of course, right? Because on and on, right? So this notebook that I'm showing here, it took several years, right, of work, right? So I guess that just what I want to say, that there is an obvious investment in time, right, to prepare the notebook, but then once you have it, it really pays off. Okay, so I think this is what I wanted to say. So thank you for your attention.
Thank you very much, Juan. That was very interesting.